Hi, my name is Austin Abbott, and I am a graduate student at the Texas A&M Cyclotron Institute in the Yanillo Research Group. My poster focuses on the work that I have been doing designing and testing the YAP cerium array for Dapper, which is currently being constructed in order to measure photon strength functions. The primary motivation for Dapper's construction is the S-process isotope iron-60, which has been measured both on the Earth and Moon despite a half-life of 2.5 million years. This is indicative of ongoing nucleosynthesis, and so by measuring its photon strength function, astrophysical models of nucleosynthesis can be better constrained. The purpose of the YAP array in Dapper is to give a time stop for a time of flight measurement that will allow us to distinguish a fusion background. So in my experiment, the target we'll be using is CD2, or deuterated polyethylene, and so the iron in our beam can fuse with the carbon in our target to create a fusion product that emits both light-charged particles and gamma rays. So in order to remove this contamination, a TOF measurement using the MCP as a time start and a YAP array stop will be used. In a simulation, we show that the DP product time of flight and the fusion residue time of flight are separated edge to edge by about a nanosecond. In the geometry section, you can see the CAD drawing of the YAP array itself, which consists of 7 YAP cerium crystals, each coupled to a UVT light guide and a 1924 Hamamatsu PMT. In both plots shown here, the percent of produced residues detected by the array as a function of this array's distance from the target position is shown for various geometries, and also for both the upcoming stable beam experiment and the future radioactive beam experiment. So the current geometry was selected due to its ability to have its position moved within the beam pipe and its much better residue collection in the radioactive beam experiment than the other geometries. And so this geometry I'm showing here is represented by the green triangles. Bases are used to provide voltage to these PMTs, and there are two different kinds, passive and active bases. Active bases are known to allow for higher saturation rates due to the inclusion of field effect transistors. So various 1355 active bases that were made for another experiment were tested in order to investigate the effects of active base resistance and the applied voltage on the saturation rate. So for this test, a beam of krypton 84 at 7.5 MeV per nucleon was delivered directly to a YAP detector, and we found that the maximum saturation rate of 1.2 times 10 to the 6 particles per second occurred when we applied the lowest voltage of negative 800 volts and used the lowest resistance active base. And so this rate that we achieved satisfies our minimum requirements, but we know that improvements could be made. And so using the information that we gained from this test, I went into the lab and built new active bases for 1924 Hamamatsu PMTs of, again, different resistance values. So for this test, a beam of copper 63 at 7.5 MeV per nucleon was used to test new high, mid, and low resistance bases. And as expected, the mid and low resistance bases achieved higher saturation rates than the high resistance base. The middle resistance and low resistance base both maxed out at 1.2 times 10 to the 7 particles per second, a factor of 10 greater than achieved from the previous test, and this is being limited due to cyclotron frequency. The decision was made to go with the middle resistance base, as the lower the resistance, the more heat is generated and damage to the base is more likely to occur. At the end of the previous experiment, radiation hardness of the YAP was investigated. The full beam of approximately 2.4 times 10 to the 9 particles per second of copper 63 was delivered to the YAP for about 10 minutes. This is equivalent to about 4 days of the rate of stable iron beam we were planning to run for our experiment. And although the integrated charge of the signals was affected as less light was produced due to crystal damage, we found that within the resolution of our electronics, the rise times of our signals were mostly unaffected. This is good as we're using the YAP array primarily for timing purposes. And so with that, I'd like to thank my group for all of their help, as well as the cyclotron staff and sources of funding which makes this research possible. Feel free to come by the poster session if you have any questions or want to know more. And thank you for listening.